everybody, it's your pal JR again, and welcome to Assume I'm an Idiot, the show where we take complicated topics and break them down into little teeny tiny chewable bits guaranteed not to get stuck in your throat. I am the idiot.
You're a moron!
And on this podcast, we'll be exploring everything from silly fun facts that everyone should know to bigger, more complicated topics like physics, metaphysics, the legal system, nature, the economy, and so much more. Broken down without corporate talk or industry speak, so that even someone like me, who's dumb as a box of hammers, can understand. So recline in your chairs, close your eyes, and breathe deeply. Unless you're listening in your car, in which case, just breathe deeply. Today's topic is one that has intrigued me since the first time I laid on my back in the yard on a summer night and stared up into the sky and thought, wait, what? But first, it's time for Random Stuff You Should Know.
Random stuff you should know!
Appropriately today, we're taking from the world of space.
Space.
The moon is moving away from the Earth. Yeah, about 1.5 inches every year. So little by little, the Earth's day is getting longer, and the effect of the moon on the ocean's tides is changing a tiny amount every day too. And in about 600 million years, when no living thing will be here anymore, there will also be no more total solar eclipse because the moon will be too far away to perfectly cover the sun. So if you've ever seen one, congratulations, you beat the clock by about 600 million years. Also from the world of space, and straight up insane, there's a planet that rains diamonds. It's called 55 Cancri E. It's about 40 light years away, and it's so carbon-rich that scientists have theorized the pressure turns carbon into literal diamond rain. So basically somewhere out there's a planet that would make a hip-hop artist weep. I wonder if we were able to get there if it would make diamonds less valuable, right? If it was literally raining diamonds, they wouldn't be all that rare, right? Okay, on to the main topic. Today we're talking about something I can't remotely wrap my head around, and if you say you can, I don't believe you. And that is, how big is the universe really? We all know it's kind of big. It's space. Space is huge. But the actual scale of it is so beyond human comprehension that when you really start digging in, your brain just kind of unplugs itself. In other episodes, I've talked about the size of the universe as quick fun facts, but never really dove into the kind of numbers we're discussing here. I fully believe the bulk of people can't even process or visualize how much a trillion is. It doesn't compute for most people. And we're talking about numbers and distances and sciencey stuff so enormous that even the top brilliant minds in the field can't fully comprehend the scale. So what chance does a thick lamppost like me have? Let me start with some basic facts I found in my very pedestrian research. And mind you, this doesn't really help me or us to comprehend the scope and scale we're talking about. These are just basic facts. In a few minutes, I'm going to talk to a very, very special guest with a brain clearly 40 times the size of mine to help break down this inconceivable math into something we can all hopefully understand. And because we have that very special guest, I'm going to keep my part of this pretty short. You're welcome. Let's start small. Our home galaxy, the Milky Way. It's about 100,000 light years across. Now, as I may or may not have mentioned in other episodes, a light year is not a measure of time. It's distance. It's how far light travels in 1 year in a vacuum. Light moves at 186,000 miles per second. So in 1 year, that's around 6 trillion miles, 5.8 trillion miles to be exact for anyone doing the math while we go along here. So roughly 6 trillion miles times 100,000 light years means the Milky Way alone is about 600 quadrillion miles across. I don't even know what that number looks like. I started to write out the zeros, and honestly, I lost count and gave up. A quadrillion sounds like a gazillion, a number a little kid would make up when they're trying to explain something. I have a quadrillion marbles. Yeah, sure, Timmy, sure you do. And that's just one galaxy, ours. One little swirl of stars floating in a ginormous cosmic soup bowl. Here's where things already get ridiculous and incomprehensible. Astronomers estimate that there are about 2 trillion galaxies in the observable universe. 2 trillion. That's 2,000 billion, each one with hundreds of billions of stars. To put that into perspective, if every star from every galaxy we know about was a grain of sand, the observable universe would be a beach a mile wide, stretching farther than you could ever walk in your lifetime if you walked every hour of every day from birth until death. And remember, that's just the observable universe, the part we can actually see. There's way more beyond that. We just can't see it because the light from those galaxies hasn't had time to reach us yet, which on its own is impossible to understand. I've seen photos of stars being born, posted by NASA, taken by space telescopes, that have a small throwaway line at the end of the description saying that this star has been dead for 5 billion years, and we're just seeing the birth of it in this photo because the light just got to us. What? What are you saying? The universe is about 13.8 billion years old, which means we can only see about 13.8 billion years worth of light. Everything farther away is invisible. Doesn't mean it's not there. The light just hasn't gotten to us yet, and I think I'm already getting a nosebleed. So yeah, there's the universe we know about, and then there's the rest, which we can't even detect. And that's where it starts to feel like scientists are flat out trolling us. Here's another brain-breaking fact. Our galaxy, the Milky Way, isn't even that big in the grand scheme. The Milky Way contains an estimated 100 to 400 billion stars, with most having at least one planet orbiting them, leading to potentially billions of planets, or hundreds of billions of planets. Everyone since grade school knows about our solar system with the big, stupid yellow foam ball sun, 9 planets, well, now 8 planets, sorry Pluto, and numerous moons, dwarf planets, asteroids, and comets. That's just our solar system. But beyond our solar system, our own galaxy hosts billions of other solar systems with diverse planets, including Earth-sized planets, super-Earths, sub-Neptunes, Jupiter-like worlds. The definition of what those things are isn't really important. But what is important is that's just our seemingly gargantuan Milky Way galaxy, wherein we reside. It sounds enormous, and it is, but there are galaxies out there hundreds or even thousands of times larger. Some are so massive, they contain over 100 trillion stars. That's a 1 with 14 zeros after it. One of them is called IC 1101. It's 6 million light-years across. You could fit 60 of our Milky Way galaxies inside of it. Not our solar system, our galaxy. Are you kidding me right now? And again, remember, everything I'm talking about is just the part we can measure. Some astronomers think the actual universe might be infinite, meaning if you flew a spaceship in one direction forever, you'd never reach the edge because there is no edge. Space itself is expanding. And here's the kicker. It's expanding faster the farther you look out, like some kind of insane funhouse mirror. The galaxies way out there aren't just drifting, they're running away from us at incredible speeds. So in theory, if you tried to travel to the end of the universe, by the time you got there, the finish line will have moved billions upon billions of light years farther away. And that is absolutely bananas. Now, some people find this depressing. Like, oh no, we're so small and meaningless. But I think it's kind of amazing. Think about it. We just happened by pure luck to live on this tiny rock orbiting an average star in a galaxy that's one of 2 trillion in a universe so big we can't even measure it. And somehow we still get mad about slow Wi-Fi and flight delays. And if you're having trouble wrapping your head around those nearly incalculable numbers, don't worry, so am I. If it helps a little, every time I think about it, I just picture space as an enormous cosmic Costco. Trillions of aisles, each filled with galaxies, each galaxy full of stars, and me wandering around lost trying to remember what I was there for. Probably snacks, but most certainly a 200-pack of AA batteries. So, how big is the universe? Is there a way to even calculate it? Is there a center? And if so, where is it? A lot of people I've met in my life think they're the center of the universe, but where is it really? Well, good news, folks. Today I am absolutely giddy to have someone who can hopefully help explain all this madness to me like I'm 5 years old, how astroscientists even measure something so ridiculously huge, and how they haven't lost their minds in the process. Someone whose smarts make me look like a single-celled organism by comparison. On the phone with us today, we have the esteemed astrophysicist, author, and speaker, CEO of the ASP, the Astro Society. That sounds really fancy. And if that wasn't enough, also host of 2 podcasts, Particles of Thought and Does It Fly, the brilliant Dr. Hakeem Oluseyi.
Thank you. Thank you for having me, and thank you for that gracious introduction.
Dr. Oluseyi, what an incredible honor.
Well, that's very kind of you.
I meant for you. This has got to be exciting for you.
It is the peak of my life up to this point, I think.
You're darn tootin'. Okay, welcome. Thanks for joining the shenanigans today. I know you're a busy man with all that incredible stuff in the intro. Before we blast off into the vastness of space, you have authored or co-authored numerous scientific books, and you've just completed your 3rd popular book titled, Why Do We Exist? The 9 Realms of the Universe That Make You Possible, which is right in my wheelhouse. I'm a science nut. So tell us a little bit about your book.
Yeah, so what I'm doing here is something that's slightly different for a science book, especially one about the universe. You know, quite often you have the scientists telling the readers, hey, here's what we know. But this time it's an invitation, right? So I do have to say what we know. And by what I'm doing is I'm laying out a cognitive map of reality, of existence. And so I go through these 9 realms, right? From the very smallest, the quantum realm, to the very largest, the cosmological realm, into weird, strange realms like the dark realm, which includes dark matter, dark energy, realms beyond horizons, which include what happens inside black holes and beyond our cosmic event horizon. And of course, we go into the speculative, which is scientifically based, the multiverse realm. And also, you know, very close to home in realms like the realm of life and the realm of imagination. And what I'm doing here is I'm asking the audience, the readers, to help us scientists, because we have gotten a lot of data and we have so many questions that now we need to bring imagination to the game.
Oh, man.
And I think that the readers are just the people who can help us out.
Right. Yeah, no, that's amazing. I say the same thing all the time, that it's sort of like data coming to us and we're going, okay, now what?
Yeah.
So the idea of being able to sort of participate in that is incredible.
Yeah, it really is. You know, we've had a lot of similar efforts, you know, of actually analyzing real data. But, you know, Galileo is known, I'm sorry to go so far back, but Galileo is known as the person that changed science in a dramatic way. And what do I mean by that? You know, we had scientists before him who were like, hey, what we believe about the universe is based on what we observe about the universe. And so we believed a lot of things that, say, Aristotle taught us because it was consistent with what we observed. But what Galileo did different was he said, let me consider something for which I could never do an experiment. For example, what happens if I remove all friction? You can't do that experiment.
Right.
And by having that single thought, he realized that an object at rest or in motion remains at rest or in motion unless acted upon by an outside force. So it takes imagination, not just data and math.
It's interesting. We one of the things we'll talk about later is going all the way back to Galileo, which we'll get to in a second.
Yeah.
So it's interesting that you mentioned that.
Interesting.
Okay, let's get into this. I'm bracing myself. I'm ready to be humiliated. Tell me, sir, everything that I got wrong.
You know, on the main, you got most things correct.
Wow. Unbelievable.
There are a lot of, you know, subtle details that sometimes can trip us up that a pedantic scientist would say, well, actually, right? But I think for the most part, as far as the broad strokes go, you've gotten it correct.
Even a blind pig finds a truffle from time to time, right?
Yeah, even a blind pig finds a truffle. That's because they're using their nose. That's not.
See, you've just proved how stupid I really am right there. So, Dr. O, here's the big question.
Okay, let's do it.
How big is the universe really?
Really? Despite what you might find from an internet search, no one knows.
Really?
That is not even measurable.
Wow. I was not expecting that.
Not only do we not know, it's impossible to know.
Okay.
But there are a couple of distances we do know. You know, I mentioned earlier these realms beyond horizons, and the universe has several horizons. One of them you got correctly, which is what we call the observable universe, right? That's about 16 billion light years from our location to the farthest distance we can see. And so that distance, 16 billion light years, is what we call the cosmic event horizon.
Got it.
Now, there's another distance you might see on the internet. They'll say 93 billion light years, but I think the better number is 46 billion light years.
Oh.
So what does that represent? Even though there are objects for whom, if they emit light today, we won't be able to see them. They emitted light billions of years ago, and today we may receive that light, even though the objects themselves are beyond our cosmic event horizon.
Okay.
So the greatest distance for those objects is 46 billion light years.
Whoa.
So these are objects that emitted their light when they were within the cosmic event horizon, but in the expansion of the universe carried them away.
Mm-hmm.
And the light is only just now reaching us today. So you will hear some people say that we can see objects that are 46 billion light years away. And that's true. But we're not seeing them as we're seeing them as they were, 14, 12, right. 10 billion years ago.
Right.
Yeah.
They could be dying, right, by now.
They could be dying. That is complicated. So I'll give you an example.
Mm-hmm.
The universe is expanding, and a consequence of expansion is that objects that are farther away from you move away more quickly, directly related to their distance. So an object twice as far away would move away twice as fast. 3 times far away would move away 3 times as fast. Even if those objects themselves are stationary, the expansion of space carries them away at faster and faster rates.
Right.
A consequence of this is that if you carry that infinitely far into the distance, eventually you reach a location where objects are receding from you at the speed of light. And that defines a horizon that we call the Hubble sphere. But because the Hubble sphere is expanding, we can see just a little bit beyond that, 2 billion light years beyond that. So the Hubble sphere is about 14 billion light years away. The cosmic event horizon is about 16 billion light years away. Okay. Now, here's what's complicated. That horizon is for light that is emitted from objects today. So if an object is greater than 16 light years away and it emits light toward us, that light will never reach us.
That's crazy.
But
crazy.
Yeah. But there are objects as far away as 46 billion light years for which we receive their lights today.
Yeah.
Right. So if they emitted light today, we would never see it. But they were much closer to us within our Hubble sphere when they emitted their light. And now the expansion of the universe has carried them far beyond our cosmic event horizon. They're now, say, 30 billion light years away, 40 billion light years away, but yet we're just now today receiving their light.
That's insane. Yeah, I've seen, I've noted before that I've seen photos posted by NASA that, show a star being born that's actually been dead, for 5 billion years or whatever. And that just absolutely cracks my head in half. Like I can't wrap my head around that,
And you shouldn't, because that's one thing you got wrong.
Oh, shocker.
We can't see individual stars very far away.
Okay.
Right. So the closest large galaxy to us is the Andromeda Galaxy, which is 2.5 million light years away. Right. So to see individual stars in an object that's billions of light years away, it's not really possible.
Okay.
So every star that you see, and this tells you how big space is, because, stars, if they are anything, they are bright. And here we are in a galaxy of hundreds of billions of stars, but we can only see 6,000 from Earth.
Right.
Yeah. And so all of those stars are nearby. They're not, billions of light years away or millions of light years away. The Milky Way, as you say, is only 100,000 light years across. So every star you see in the sky is still there. There's not a single star you're going to see that is already dead.
All right.
Unless it's on a very short time scale.
All right. I've been fooled once again by social media. I've been I look at that, I see it, I believe it, I nod my head.
That's a common one.
Yeah. No kidding.
You're not alone. Yeah. Yeah. And by the way, those objects, that distance of 46 billion light years, we call that the particle horizon, because that's the greatest distance of objects whose particles, like light particles, other radiation particles, we are receiving today.
So does that apply to images taken by the James Webb or the Hubble?
Well, if you're looking at the very, very deep universe, like the James Webb Space Telescope is able to do, it does apply.
Okay. So I can see through those images that I see from the James Webb or the Hubble, it's possible that I'm seeing a star that by the time I've seen this photo, that star is now dead or has gone supernova or whatever.
Well, generally, when you're looking at the deep universe, even if you're using the James Webb, you still don't get individual stars in the very deep universe. You just get a smudge of a galaxy, okay? And in that smudge of the galaxy, that light that you're receiving does originate primarily from stars. And the stars that are emitting that light, yeah, chances are the biggest and the brightest ones are the ones that stand out in the image. They only last a few million years. So they're probably long gone. They're definitely long gone.
So I am not as stupid as I thought, or even you thought. So that's great. That's good news.
You couldn't possibly be.
Right. You couldn't be more stupid than I thought you were. Okay, so speaking of the James Webb, I just read an article. I don't know anymore what's true and what's not, right? I'm reading articles that claim to be from NASA or from James Webb or whatever. But the article that I just looked at was James Webb telescope spots galaxies that may be older than the universe. And I'm like, say what now? What is this inconceivable nonsense?
Exactly.
So how could something be older than the universe if this is even possible or true?
Right. I saw that headline as well. So let me tell you what I think. I didn't read it, but it reminds me of a problem we used to have. Okay. And that was orbiting our galaxy, there were stars that appeared to be older than the universe. Okay. And so we had the ages of the stars correct, but we didn't have the age of the universe correct. All right. And so once we got better measurements of the age of the universe, now the stars were no longer older than the universe. So what they're saying is something along those lines, I'm sure. So how we get to the age of the universe is complicated, right? We don't just say, hey, universe, how old are you? And they're like, oh, I was born on January 1st, 0. It doesn't say that to you. You got to tease it out based on a lot of different measurements. And the same thing with the ages of galaxies. You have to tease it out. And typically we use stars in the galaxies because we understand how stars age. And so there are different relations we have that we can use the stars to age the galaxy that the stars are in. So something in those methods is giving a paradoxical answer, but it is impossible for the galaxy to be older than the universe as far as everything we know goes. Because one of the non-negotiables of the Big Bang, in the early days, there were different models of where does the matter in the universe come from. There were models that were leading that suggested that matter was always being created in the universe at all times. But then there was the idea that it all came into existence in a moment, right? Since then, the in a moment has won out big time. So there would be no matter to form a galaxy before the birth of the universe.
Gotcha. That was very, very eloquent, and even I understood it, which is saying something. That's great.
You're smarter than you think you are.
That's entirely possible. To be fair, that's a pretty low bar. All right. So this leads me to, setting up with a story. When I was in grade school, a teacher would put a marble at one end of the hall and a basketball at the other, and told us this was about, quote unquote, the distance of the Earth to the sun.
Yeah.
And we all kind of went, cool, when's lunch? Or we did the foam painted ball solar system with everything 7 inches apart, right? So most of us have no sense of scale of our own solar system, let alone the universe.
Right.
So the question becomes, how do we actually measure it?
Yeah, so there's two things. One is envisioning it, and the other is actually measuring these distances. Mm-hmm. So to envision it, for example, the way to think about whether something is close or far by is in terms of the sizes of objects. So, for example, if you look at the Earth-Moon system, the moon is about 1/4 the size of Earth. So I'm a dude who's like 8 feet tall. So that means that 1/4 of my height is 2 feet. Okay. All right.
Yep.
So if you want to imagine the Earth-Moon system, imagine, the tallest 8-footer in the world with a 2-foot toddler standing next to them. That's the Earth-Moon.
Okay.
But now, in terms of the distance away, the moon is about 65 Earth radii away.
I see.
So the radius is the distance from the center to the edge. So for a 8-foot tall guy, its radius, let's call that 4 feet. So what's 60 times 4?
Are you asking me? You know better than that.
Right.
No clue.
Okay. That's 240 feet.
That's exactly what I was going to say.
Right.
Sorry to interrupt.
Okay. So that means that you take that toddler and put them 240 feet away from that 8-foot tall giant.
Right.
And now you have the Earth Moon system.
Okay.
All right. If you look at the sun is about 100 times bigger than the Earth. Right. And the Earth is like 200 solar radii away from the sun. So let's say, for example, that you are I'm 73 inches tall, personally, right? 6'1". So 1/100th of my size will be 3/4 of an inch. So imagine 3/4 of an inch, a marble standing next to a 6'1" man. Now, if you want to put it 100 of my radii away, let's say 100 times 3 feet. That's pretty much a football field away. So if you want to imagine the sun-Earth system, take a 6'1" man, stand him in one end zone on the 0-yard line, and take a 3/4 inch marble and put it on the opposite end zone 0-yard line. Right.
So what you're saying is,
know that marble. Yeah.
What you're saying is Mrs. Nelson was wrong all the way around. The basketball marble.
Well. Well, she probably was careful with how she used the word.
Yeah, that's
but the
true.
thing to note is that 6'1" man doesn't even know that marble is there 100 yards away, right? I mean, yeah. So that's how the sun thinks of the Earth. You're a nothingness out in the vast expanse of blackness,
right?
So how do you make the measurements? So the way we make measurements depends on how far away something is. So the most direct way is by geometry, triangles.
Math. My arch nemesis. Okay, hit me with it.
So you know that if you look at a nearby object, say you and someone else are some distance apart, and you look at a nearby object, you're going to have different perspectives. So that means that the object's going to be in a different location relative to the background, right? That whole thing about triangulation. So the first time we really knew the size of the solar system happened in the 1800s. There were solar eclipses where Venus passed in front of the sun. So different people on different parts of the Earth would see Venus cross in front of the sun's disk or out of the sun's disk at slightly different times. And you could triangulate how far away Venus was based on that. So, when 1800 came up, we had no idea how big the solar system was. But by 1900, we knew. Now, here's the thing. When you get far enough away, that whole relative to the background method that we call parallax doesn't work anymore because the changes are too tiny. Right. That's why an airplane looks like it's moving slow when it's far away in the sky, whereas a car right next to you feels fast, right?
Right.
But what we can also do is there are certain stars that we know how bright they truly are. And what we know is that objects dim in a particular systematic way the farther away they appear, right? And objects also look smaller. So if you know how bright something really is, you can compare it to how bright it appears to be and calculate its distance. If you know how large something really is or how far on average galaxies are separated from each other, then you now have a size that you can compare to, what we know to be true versus the way it appears. So that's pretty much the main methods that we use for most of the universe.
Okay. Got it.
And that's how Hubble discovered that the universe was expanding, right? He looked at these pulsating stars in Andromeda and calculated their distance because he knew how bright those pulsating stars were. A woman named Henrietta Leavitt had figured that out. They're called Cepheid variables. And so by comparing the brightnesses of these Cepheid variables as they appeared to how bright we knew they happen to be, he realized that these things are millions of light years away.
Right.
Most astronomers thought Andromeda was a cloud of gas within our galaxy. So that changed everything. Yeah.
How did they calculate the speed of light way back then? For everyone listening, the speed of light is 186,000 miles per second. Correct, Doc?
Right.
So how did they calculate that when there weren't even, as far as I know, stopwatches at that time?
Yeah, so the very earliest guy to do it was someone named Olaf Romer. And so what he was doing is he was applying the Newton's laws of physics to the motions of Jupiter's moons.
Whoa. Time out. Okay, hold on. Hold on there. Let's hold on there, Brainiac. Let's back that one up a little bit. Just slow it down and explain it for a moron like me.
Yes, sir.
Pretty please.
Okay. So the moons of Jupiter are orbiting the planet. So from our perspective, it looks like they're moving back and forth. And they will slip behind or in front of Jupiter from time to time.
Mm-hmm.
These are eclipses of Jupiter's moons. So Newton's laws would allow you to calculate at exactly what time those eclipses should occur. And what he found was that in many cases, the calculation was given the wrong answer. Sometimes it was a little bit before, sometimes it was a little bit after. And he realized that, you know what? It seems like when the answer is a little bit before what I expect is when Jupiter is close to Earth. And when the answer is a little bit later than what I expect is when Jupiter is farther away from Earth. So maybe the difference is based on the time it takes light to travel those distances.
Okay.
So he put that into his calculations, and voila, he got the very first measurement of the speed of light, right?
Unbelievable.
Yeah, unbelievable. But since then, we've come up with far more sophisticated ways. So one way is to have a rapidly spinning mirror, right? And you will shine a light toward that mirror, and that mirror will turn a little bit. And that means that the reflected light will come off at an angle relative to the original light. And so, as a result, you can calculate how fast the light is moving.
That's incredible.
Yeah.
So way before computers, way before when we're talking about Galileo, now I'm assuming there's supercomputers somewhere the size of an airplane hangar that are doing a lot of these calculations because we have the basics already sort of input. So before computers, it was literally math. That was it.
Exactly. So it's interesting you mentioned Galileo because he attempted to make a measurement of the speed of light. Him and his assistant took 2 lanterns on top of these 2 hilltops that were separated by a few kilometers. And the idea was, I'll turn on my light or open the shutter on my lantern. And when you see it, you open your shutter. And we could calculate using our pulse.
Yeah.
Right? They were feeling their pulse to time the speed of light. And what they figured out was, the speed of light is really fast.
Yeah, because and then your pulse changes in races. The more excited you get about the speed of light calculation.
Yeah, and you couldn't keep. The distances. Think about it. Light travels 300 million kilometers in 1 second.
Yeah.
So your few hilltops separated by less than 10 kilometers, you're not going to be able to see any difference.
So if the universe is constantly expanding, as you said, the further you get out or the further it's away from us, the faster it's expanding.
Yes.
Are we kind of using, are any of our measurements extrapolations? Meaning, are we kind of using a guesstimate? If it changes every minute at incredible speeds, how are we keeping up, as it were, with the new measurement that's happening second by second?
Yeah. So the thing about this is that, you're getting into the fine details.
Sure.
And so we still have certain questions, right? So right now people are saying, hey, we got to do this with more granularity. For example, we treat the universe like it's one big gas of galaxies that's uniformly distributed and is expanding at the same rate in every direction. We haven't actually measured that to be true.
Okay.
But thank goodness we have this new telescope called the Vera C. Rubin telescope that is going to make so many measurements around the sky that we might be able to get what we call pencil beams or laser beams to measure expansion, with a high enough statistical certainty in various directions to see if there is any change. Right. And not only that, another measurement we've never made is observing a galaxy's redshift, as we call it, change in real time, right? What we call redshift drift, right? So you should see it getting bigger with time, or moving faster with time. And that's a very sensitive measurement that's very difficult to make. So yeah, there are fine details in the process of the universe's expansion that we don't have the knowledge of. And so whenever we make these big statements about the nature of the universe, we have to make some, I'm going to use the word assumptions, but they're not purely guesses because they're bounded by data.
I love
it. So we have different probes that we use, right? We can use supernovae. We can use this light left over from the formation of the universe called the cosmic microwave background radiation. We can use the
Wait. Hold, time out.
Okay.
Hold it. Slow your roll there, Professor.
He doesn't understand.
I'm sorry.
Explain as you would a child.
Okay, so let's talk about that. Let's talk about what you were just saying, the leftover light.
Yeah. So basically, what the thing that convinced astronomers and physicists that what we call the Big Bang, meaning that the universe was small, hot, and dense, and it has expanded ever since, that was true, was when this light that was discovered by Penzias and Wilson in the 60s, but measured very carefully by Mather and Smoot in the late 80s, early 90s, and all four of them won Nobel Prizes. That convinced us when we got this careful measurement from the Kobe satellite by Mather and Smoot that the Big Bang was real. And so what is that? Well, if you're in the military, you have these infrared goggles, right? And so people at night look bright in infrared goggles. And the reason why is because opaque objects like ourselves, we emit light, all of us. You're emitting light, I'm emitting light, the phone in your hand, the microphone, the desk, they're all emitting light.
Ooh,
okay?
That's cool.
And the light that it emits, the color and intensity depends on the temperature of the object. So cool objects like us, you and me, cool objects, right?
Sure.
We emit infrared light. You take a bar of iron, you start to heat it up, you see it starts to emit red light. You heat it more, it gets white hot, right? So the thing about that light that is emitted based on temperature of opaque objects, it always has a very particular shape when you plot its energy versus the energy density versus energy, or intensity versus wavelength. It always has this shape that looks like this bell curve that's kind of lean to one side, right? It's called a black body curve, right? So we know that only certain objects emit this light. So when these guys measured the spectrum of that light, it had that exact shape to greater precision than any other object we've ever measured in the universe,
Gotcha.
right?
Yeah.
So get this, only opaque objects emit it, and it is the most precise one we've ever measured. So either everywhere in the universe was opaque, meaning the Big Bang was real, or there's actually a surface out there that is opaque that is emitting that light.
I got you.
And so based on the intensity of the light, we can predict how far away that surface should be. And what we find is that it should be a shell surrounding the Milky Way galaxy at about 200,000 light years away. And if that was true, we would not be able to see any other galaxies, but we do.
Okay.
So we know that that is not the correct explanation. So the only explanation is that the universe everywhere was opaque. But then there's another 14 other observations that we predict that if this was true, if the Big Bang is real, then we should observe this when we go look. And we've gone and we've made all those observations. And in each case, they're true to a very high precision.
Gotcha. I think a little bit of blood trickled out of my ear during that because my brain is exploding.
I hope it's a good explosion.
Yes, it was very beneficial explosion. Any explosion in my brain is beneficial.
All right.
As I mentioned at the top of this episode and maybe in other episodes, I think most people can understand a million of something. That's an easy thing to understand. I think fewer people.
I don't know.
Really?
Yeah.
Well, I think
fewer
people
is way bigger than I think people think. Yeah.
Well, yeah, but I think fewer people can comprehend a billion of something. I think that's really very difficult.
Oh yeah.
I think
right.
A minuscule amount of people can visualize a trillion of something, whether that's $1 trillion or a trillion rubber bands for all that matters.
Yeah.
They vastly underestimate how much that really is. So when you start talking about quadrillions, quintillions, whatever comes next, a Googleplex, even some scientists must have a tough time digesting some of those numbers. I'm imagining some of them are even having their minds blown on a daily basis.
Man, we got tricks. And I'll tell you what's so awesome about this is that once you get these numbers in your head, like the numbers I was telling you about the size of the Earth versus the moon and that sort of thing,
right.
You have an intuition in your mind. You have an intuition about how big things are based on how far away they are. So once you know the moon's real size and its real distance, you can see the moon as it is and see how massive it really is. But in the same way, you can see galaxies like the Andromeda galaxy, which is 2 million light years away, but yet it's 6 times bigger than the full moon in our sky, right? 6 times bigger than the full moon in our sky. So imagine, at 2 million light years away, how monstrous that thing must actually be, right? So us scientists, we use the phrase orders of magnitude to describe things. So we'll say, for example, oh, the size of the atom is 10 to the minus 10 meters, and the size of the Milky Way is 10 to the 20 meters. So all we care about is the minus 10 and the 20, and that gives us sort of a mental picture, right?
Gotcha.
Now, can you envision it? You don't have many opportunities if you're not looking at the night sky, or you're not looking you're not using the electron microscope every day, or a transition, a TEM every day, right? So experience helps you, and dealing with numbers in a way that, typically you're only developing intuition for when you're actually doing science and engineering, right? The world doesn't really offer us opportunities to practice these skills. But let me tell you this, man, even when you are given the opportunity, for most of us, it's when we're graduate students and undergraduate students, it still takes years
I can imagine.
For you to develop a real, mental model intuition around these things.
So I have a question then that comes out of that. And, if we're basing a lot of this on we know the size of the moon, I'm going to pretend to be smart for a second. So just hold on to buckle your belt. Sometimes light is bent, right? So sometimes the moon looks absolutely enormous, even though it hasn't changed size or gotten any closer to the Earth. So maybe there's not a direct answer, but how did scientists prior, in years prior, absolutely lock in the size of the moon based on that? If light can bend and make the moon look bigger, how did they sort of account for that?
Man, look, humans are smart. So, if you look at history, the first person to try to make these measurements was a cat named Hipparchus back in ancient Greece.
Okay.
And then you have a cat named Eratosthenes, who makes the first accurate measurement of the size of the Earth back in ancient Greece. So, once you understand triangles, so, when you look at the invention of mathematics, right, you have arithmetic first, because they had to account for things they were counting, grain, horses, maybe not horses, grain, things they're trading, right? But then also they need to measure land and make buildings, so they invent geometry. But then you wanted to measure the sky, so you invent trigonometry, right? And that's based on triangles. And so just using the science of triangles, you can figure out a whole lot, man. And these ancient people did it, and recognize they didn't have social media. I remember my life as a country boy in Mississippi. Life was slow.
Right.
You had a lot of time for deep thought. You had a lot of time to sit around and stare and calculate and wonder and ponder, And given this human brain, we just build one on top of the other. And now we're at a point where, if I want to go to an observatory and observe a particular star, I go to a star chart and I look up the coordinates of that star. But if I were to point directly at those coordinates, I wouldn't get the star, because if it's low to the horizon, for example, I have to calculate refraction in the air. So the atmosphere, just like when you have a spoon in a glass of water, it makes it look like it's broken off, right? It changes the direction of the light. The atmosphere does the same thing. So I have to do that calculation to get the actual pointing. But we're so good at this now that we all do it without even a second thought.
Sure.
It's kind of like how GPS has to take into account relativity to give you an accurate measurement on Earth. Oh, man, we are so advanced with this stuff now that we take it for granted. We just take it for granted.
Did I make myself sound smart by even asking that question? Because I feel pretty good about myself.
You absolutely did. And what you did is something that happens a lot when you get into thinking about this stuff, is that you discover what's already been discovered independently. You're like, oh, I'm on to something. And then you go tell someone, they're like, oh yeah, that's Taylor series you just rediscovered, right? But the fact that you figured out what some great scientist figured out, that says something.
I'm gonna take that to my grave. Thank you so much. So that leads me to something else I mentioned. Which is the idea of infinite. I've heard some physicists believe that the universe is infinite. You can tell me whether that's true or not. How do people even wrap their heads around something that's infinite? I mean, everybody lives in a confined space reality, whether that's your street, your state, your country, your planet, or even your solar system, which is really pushing it. So how do we, both fools like me and the scientific community, comprehend something like infinity?
So the first thing is, let's get down to the basics of what infinity really means.
Okay, hit me with it.
Infinity isn't a number. It's just a word that means without end.
Yep.
All right, without end. So if you've ever been at the within earshot of a screaming baby, or doing something miserable, or you're in the military and your troop is being punished, so we're gonna run for a gazillion miles. You know what it feels like without end.
Right.
you know that feeling, right?
I've been there.
But the thing about the universe, when you apply infinity to the universe, it's even weirder than you mentioned, because it's not just that the universe itself may be infinite. It's that there may be an infinity of universes.
What?
Yeah, like I talk about in my book, right? The multiverse realm. When you study the very origin of the universe, you're led to this idea that came about in the 1980s called inflation. And one consequence of this idea, when you look at what the data says about what might have caused it, then what you realize is it may be happening all the time. And the universe, the greater universe outside of our universe, may be just popping out universes nonstop.
That's crazy.
So there's a book about it by the professor Will Kinney, and the title of it is An Infinity of Worlds, because that's the implication that our universe. And so when physicists say that our universe may be infinite, there is no observation that says, I have measured the universe to be infinite.
Right.
So we can't accept that that is true. Okay. But what we can say is that, hey, when we look at what we know about the universe, being infinite versus being finite are both consistent with the data.
Right.
There is nothing in the data that says it has to be one or the other.
Gotcha.
So that means you cannot rule out an infinite universe.
That is mind-blowing.
Let me tell you something. But what we also know is, based on this idea of inflation, is that our entire observable universe is a tiny fraction of the universe that is beyond our universe. A super tiny fraction. A tiny little dot in this vast.
I mean, it's something that, John Q. public cannot get their head around. I mean, there's no way, even if people wanted to know, I could research this and study this forever. And just the sheer math of it and the idea, this kind of speaks to a little bit philosophically about how important we are in the grand scheme of things, right? Everybody's got an importance.
Yeah.
But, when you're talking about unbelievable numbers and unbelievable, math, which is incredibly impressive, it's just one of those things that's like, maybe I'm better off not knowing. It's one of those kind of things, right? Maybe I'm better off not knowing. Maybe it's just going to confuse me more than I already confused.
Well, it is going to send you down a pathway of thought that can get, existential.
Listen, I've got a limited amount of thoughts, so I got to use them wisely. I can't be branching off into all kinds of different things. Okay, so mathematically speaking, Is there a center of the universe? And if so, where is it?
Mathematically speaking, there are no special locations in the universe. No center, no edge. And so we have a phrase for this state of being. We call it the cosmological principle. And the cosmological principle has the consequence that the universe is what we call homogeneous, means it's made of the same stuff everywhere, and isotropic, meaning that there are no special locations. Okay. So, for each human being, the center of the universe is right inside our own heads.
I was going to say, I need to call my sister and tell her I was right all along, that she is not the center of the universe.
Yeah, but like I point out in my book, you may not be at the center, but you are in the middle in terms of scale, right? Sure. If we look at the largest known scale of the universe, it is the size of the observable universe, which is 10 to the 26 meters. And the smallest known physical distance is that associated with a subatomic particle called the neutrino, which is 10 to the minus 26 meters. So between 10 to the minus 26 meters and 10 to the 26 meters is us at 10 to the 0. And for the pedantic listeners, I'm speaking the logarithmic middle here.
Wow. I'm going to go out on a limb here and say we don't have a whole lot of pedantic types listening to this show. So this might be a little philosophical, but we were talking a little bit about, infinity. But what was there?
Yes.
Is there an answer? But
Yes.
what was there before there was a universe? And again, this speaks to the human brain trying to
Right.
understand a concept like nothingness.
Exactly. So it isn't nothingness. That's the thing, right? The Big Bang, our origin of our universe is not the beginning of everything. So when you look at the universe fundamentally, this might be a time for a sound effect. Albert Einstein said this, allegedly. I haven't confirmed to be true. But what we understand from what we call particle physics, the study of the very small, the foundational level of the universe, is that fundamentally, the only thing that exists are what we call quantum fields, fundamental quantum fields. So when you think of like an electric field, a magnetic field, a gravitational field, it just means something that has a value everywhere in space. All right. So these fundamental quantum fields and energy. Now, for fields to exist, you need a geometry, a space of some sort. And for energy to exist, you need time, because energy creates change. That means you need a before and an after. So in our model of the universe that is born out of our observations and best knowledge of how the universe works, this thing known as the inflaton field, which birthed our universe, existed before our universe. So energy existed and fields existed before our universe, which means that there is a time before time. And that inflaton field still exists. It is a more fundamental reality than our own reality, right? In the sense that it continues to birth new universes. It may have been doing it for an infinity before our universe was birthed, and it may do it for an infinity after, right? And so, these universes continue to nucleate out of this inflaton field. So, yeah, it's a different perspective today than we had, at the time you and I were teenagers.
Right.
Yeah.
I like the word nucleate, by the way. I'm going to start putting that in common conversation. Okay. So I read a lot, true or not, I read a lot of articles and theories about, quote unquote, this is how the universe will end, which usually equates to this is how our solar system will end, or our Earth will die.
Right.
Is it even possible to determine if the universe could end? I don't think it could, but and if it could, what might that look like? Sort of a Big Bang Part 2?
Well, it depends on how you define end.
Oh boy.
So the what happens is that, when you create these ideas for, the nature of the universe, you write down some equations. And if you look at the equations of physics, they typically tell you how something changes with time, right? So we have these equations that we call the Friedman equations, Friedman-Einstein equations, that describe how energy evolves in the universe over time, how the size of the universe evolves over time. And what we find is that the universe responds to what is inside the universe. And the stuff, so essentially, because the size of the universe is changing, the relative amounts of the different stuff that make up the universe changes also. And so the stuff is in three broad categories. All right. There's stuff that has mass. And the thing about things that have mass is that they move slowly through space and rapidly through time.
Okay.
Then there's stuff that has almost no mass or no mass, and it moves rapidly through space, stuff like light, gravitational waves, and almost not at all through time.
Whoa.
Right? And then you have space-time itself. Okay. And so each one of these three things has an energy density.
Okay.
Whoa.
Hold it.
Remember, I have the intellect of a housefly. Let's back it up. Please explain for morons.
All right. So I forgot the original question.
Who's the idiot now?
JR, you tripping, man. So what is the future?
Right.
So here's the thing. Since dark energy became dominant, the universe is expanding ever more rapidly.
Okay.
So that means that as it expands, it gets colder. How far you can see. So one reason why I think the universe is still it's still super young is because in the not too distant future on cosmological time scales, every galaxy cluster that's not in our own galaxy cluster is going to be beyond our cosmic event horizon, and we won't be able to observe them. Yeah. So we won't. So only a young universe is even observable. So what happens in the distant universe? The stars in the distant time, right? The stars will die. The galaxies will all coalesce into one or two supermassive black holes, and the universe will become cold and dark. So we call it a heat death. So talk about big numbers. We're talking about 10 to the power 100 years away.
Okay. Gotcha. So again, that's one of those numbers that, someone like me starts writing and just gives up. And it was like, no, I don't know how many zeros that even is. So I'm going to stop right here.
That's why we use that math trick, man.
Right.
You can't write down all those zeros.
Right. Okay. Right. So that leads me to a great big fat question. And that is why? Why do we want to know? And I need to tee this up a little.
Okay.
Not in any way to belittle what you do for a living or your unbelievably brilliant work and giant brain. But how do you explain the why to John Q. Public? That it's for research, right? I recently did an episode about humans going to Mars and talked about the way it's sold to everyone. Humans on Mars has always been sold as a backup plan, Earth 2.0.
Right.
Because the idea of pure research does not interest 99% of the population. So unless it has some kind of value, most people are like, who cares?
Right.
Now, I'm admittedly a complete buffoon, but even I know that one discovery leads to another discovery leads to another discovery, and eventually it's something that would help us here.
Right.
Why do we want to know this information? Please connect the dots for all of us like we're third graders.
Right. That's a hard thing to do.
Okay.
Because those dots are long. So take, for example, what I mentioned earlier about how when you heat an object, it emits light.
Okay.
All right. Scientists were thinking about that at the end of the 19th century. Okay. Mm-hmm. We got our answers by the beginning of the 20th century, and that led directly to the smartphone.
What?
Yeah.
Is that true?
Yeah. Because in order to answer that question, you had to figure out fundamentally what is matter. You had to discover the atom. You had to discover electrons and protons, the atom's energy levels. Then, like one question I love to ask people is, where does light come from, right? Most people say the sun. And when I point out to them, when you're in a room at night, there's light in there, but it's not coming from the sun. Where does it come from?
Right.
A lot of people will then say energy, to which I will respond, no, light possesses energy. It does not come from energy. And then I point out to them, the easy answer is matter makes it, right?
Okay.
And when matter makes light, the signature of what the matter is and what the matter is doing is encoded in that light, right? So by understanding the fundamental nature of matter and electrons, we discover these things called semiconductors.
Get out of town.
And we're able to build these devices called transistors. And that leads to computers, which leads directly to our smartphones, right? We discover things like giant magnetoresistance, which allows you to have, back in the day, you had a big giant floppy disk with 1.44 kilobytes. And now you have a microscopic chip with terabytes.
Right, right. Well, so the example is, I just read a few days ago, and, this could be another internet nonsense, but a planet called LHS 1140b. Okay, so what it's claimed to be is one of the most Earth-like planets we've ever found.
Right.
But it's 49 light years away. If my math is right, it's 2.8 trillion miles away. Okay.
Right.
So it's cool that we found it. I always say, that's really cool. But we can't get there. So why is that discovery / identification important? What does that mean to where we came from and, what our future might be, et cetera?
Okay. So imagine you were asking someone in the early 20th century, right? Albert Einstein, he figures out what's called the photoelectric effect that has to do with how matter absorbs light under certain circumstances, right? And some reporter asked him that. Would he be able to say, oh, well, in the 21st century, 100 years from now, we're going to have a computer world. We're going to have these devices called smartphones with cameras that use not film, but pieces of semiconductors to record the light.
Right.
Could he have possibly have said that?
No way.
No, he could not envision that. So what we've learned over time is that those who invest and perform fundamental research, those nations are going to be the winners. But there is a second element to it, right? Because if you look at all of the advances in electricity and magnetism that occurred in the 19th century, it occurred primarily in Britain. But yet, Edison was the guy, an American, who put lights around the world, right? Mm-hmm. Paris had lights, the city of lights, before London did. So it's not just doing the research, it's having this ecosystem that includes government, which to me means the people, investing in fundamental researchers who are primarily at universities, who then have a handshake between the government and private industry to take advantage of these innovations.
Gotcha.
But even then, like if you'll notice, quite often there are things that are invented in the United States, say the automobile, but then later you find that, Germany is kicking your butt, Japan is kicking your butt, now China is kicking your butt, right? So that has to do with, an ecosystem. It has to do with how business is done, as well as how government and investment are done, as well as how research is done. Okay. So, America was excellent in the 20th century for creating this infrastructure and this ecosystem. And now we must continue to take advantage of it going into the 21st century. And if you make these investments and you create this infrastructure, you're going to dominate the 21st century and so forth into the 22nd century.
Amazing.
Yeah.
Everything you say gets more and more amazing. Okay. And since you've said so many amazing, astounding, mind-blowing things, before I let you go,
yes,
give me your favorite little-known, mind-blowing fact about the universe, or space, or Earth for that matter. Just something that's like, oh my gosh, I can't believe that.
Okay, so I would say this sometimes to my students just to, do a nerd brag, right? It's kind of like, certain jokes, right? Like your mama jokes, blah, 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 right? But when you do them in the nerd realm. So, typically my research students, the phrase is something like, man, I'm so badass, I breathe the cores of dead stars, which is true.
Okay.
The oxygen that you're breathing was created in the core of a dead star. The carbon dioxide in our air, those carbon and oxygen molecules, they were created in the core of a long dead star. So yeah, man, I breathe dead star core.
So when someone says you're made of stars, it's absolutely true. We're made of stars.
You're made of stars, but you're also made in a Big Bang, right? Because, there's a lot of hydrogen in your body, and 3/4 of it was created, at that time when the cosmic microwave background radiation was created that we call hydrogen recombination. So that goes back to, 380,000 years after the universe began. So, you're made up of stuff that was created in the cores of stars, in the atmospheres of stars, during the Big Bang, and some elements that are created just out in space where, an alpha particle slams into an element and breaks it apart, and now you got some lithium, right?
Right. Well, see, now I had that.
It's many processes.
I had that perfect poetic ending, and then you just had to ruin it with the Big Bang. I was so good with the stars. It's so
too simple, man. You're the one who brought in the granularity and the detail. I'm feeling your vibe.
All right, I'll own that. That's true.
All right.
Well, Dr. O, this has been an absolute genuine thrill for me. I am a huge fan.
Thank you, sir.
Can't thank you enough for joining our little circus sideshow. I hope you had a good time.
Excellent time. Thank you so much.
All right. So Dr. Hakeem Oluseyi's book, Why Do We Exist? The 9 Realms of the Universe That Make You Possible, is it out now? Is it available now?
It comes out on April 21st. But you can pre-order it right now. Great. And I encourage you to do so. Thousands of copies, dozens.
The perfect gift year-round for any occasion.
Absolutely.
Please give a plug for your podcasts, plural.
Yes. So the Nova podcast is called Particles of Thought. You can find it on all audio platforms and the video version on YouTube. I talk with brilliant scientists, and it is an amazing podcast. It hit number 5 nationally in science podcasts.
Wow.
But also, I'm a big fan of science fiction, and I was raised on Star Trek. And lo and behold, I grew up to collaborate with Roddenberry, who are the Star Trek creators. And our podcast that I do with my co-host Tamara Krinsky is titled Does It Fly? And we examine science fiction in movies, in television. I talk about the science, Tamara talks about the story, and in the end we talk about the vibe, and we decide, could this exist in the real world?
Wow.
And if it did, how would it come about?
Man, that is up my alley. I am a science nerd, Nick.
Love it.
My wife and I met over Star Trek. We are massive fans.
Oh, no way.
Yeah, for sure.
Yeah. So you can find us on Instagram, TikTok. We have a website called doesitflypod.com.
Awesome. Dr. O, A real honor and pleasure.
Thank
You
you.
are now a friend of the
All
show.
right.
So sadly, that
Thank
means
you.
you have an idiot for a friend. So please
I can
come.
live with that. Yeah.
Okay,
Yes, sir.
please come back anytime you want to get away from those stuffy brainiac science people and just chill out with us, okay?
I appreciate you. Thank you so much.
That does it for this time. Appreciate you listening. Thanks so much to our special guest, the fantastic Dr. Hakeem Oluseyi, who definitely made my brain hurt, but in all the best ways. Please check out his new book, Why Do We Exist?, which sounds amazing. Appreciate you trying to help me understand this stuff. I'm not sure it worked, but then again, you are starting with a very blank slate, so thank you. Got a topic you really want to know about? Want to tell me what a complete buffoon I really am? Or maybe you just want to say hi. Email us at hello@ruffandtumble.com. That's hello@ruff-n-tumble.com. Join me for another upcoming episode of Assume I'm an Idiot. I'm your pal JR. Catch you again soon.